Hi, for this video, we will be talking about the stoichiometry roadmap if the chemical reaction that we are dealing with involves gaseous substances. So when we talk about gaseous reactants, you know that there are some gas laws that governs them. And this time, in the previous video, you know that you did the ideal gas law in which it was a PV is equal to nRT. Now, that previous knowledge, we're going to apply this to our stoichiometry roadmap and make it as one of the equations that we will be using when the equation involves gaseous substances. So now let's discuss the stoichiometry roadmap. This was the stoichiometry roadmap that I showed to you in the previous videos. The only difference now is with the moles. If you look at moles of A and moles of B, there's an extension to each of the side. It can be the volume of gas B or volume of gas A. Now, when we talk about volume, this is an assumption that either A or B or both are gaseous substances. So in that case, if we are dealing with stoichiometry related problems and in which you are asked for the volume or other gaseous physical quantities that you need to solve, usually it's within the mole quantity, the mole unit of either the given or the required substance. Now, how do we get the volume of gas B or some other factors like pressure or temperature, or the other side also, same thing, volume, pressure, temperature, and so on and so forth? How do we go about that? There are two ways. Just remember these two things. If you will see in the problem that the condition for that substance is at standard temperature and pressure, or it has an acronym of STP, it means that 1 mole of an ideal gas, in which our assumption is our gases are also behaving ideally. So 1 mole of any gas that behave ideally occupies a volume of 22.4 liters. So that means this is now a conversion factor. So again, every time it is mentioned in the problem that the condition is at standard temperature and pressure, you can safely assume and accurately assume that 1 mole of any gaseous substance will have to have a volume of 22.4 liters. So it's a conversion factor in which you can put a 22.4 on top or below depending on what you want to cancel out. Just an FYI, what do we mean by standard temperature and standard pressure? The measurement of that is standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere, in which atmosphere is shortcut as ATM. So 1 atmosphere is 1 ATM. It's not read as atom but atmosphere, ATM. So that's one conversion factor. 1 mole of any gas occupies a volume of 22.4 liters at STP. So that's one conversion. Second approach is the ideal gas law equation that you just learned in the previous videos. So ideal gas equation is PV is equal to nRT, in which you just have to find out what are you looking for, what that equation is for, what variable you're looking for, and what are you given, so that you can transform the formula and get what you need to get. Always remember that if you're dealing with ideal gas law equation, this is not at STP anymore. It's other conditions that will be stated in the problem. And remember also that you need to memorize the R value, which is 0.0821 liter atmosphere per mole Kelvin. So take note, there are two things only that you need to remember when you're dealing with gaseous conversion in stoichiometry. Either the STP, which is 1 mole is to 22.4 liters, or if it's not STP, you're going to use the ideal gas law equation. So let's now be ready to apply this in one problem here. Let us apply this in the problem of ozone. Okay, here. Let me show this to you first. The different conversion factors that you might be using when you do some gaseous calculations. So when it's pressure, these are the common conversion factors. 1 atmosphere is 760 torr. 1 atmosphere is 760 millimeters mercury, and 1 atmosphere you have 101,325 pascal, and 1 kilopascal has 1,000 pascal. Take note that these conversion factors are very useful because in the ideal gas law, your pressure has to be in atmosphere. So if you're given other pressure units, you need to convert it to atmosphere first. And then for temperature, for those who forgot about it, remember that every time you're dealing with gas loss equation, temperature unit has to be in Kelvin. So if it happens that you are given in Fahrenheit, your Fahrenheit has to be converted to Celsius first, and then Celsius to Kelvin here. So take note of this formula that you need to remember. So for Fahrenheit to Celsius, all you need to remember is the Fahrenheit value, subtract it by 32, then you multiply it to 5, then divide it by 9. After getting the degree Celsius value, then you're ready to add it by 273, or sometimes it's 273.15 or 0.15, so that you will get the Kelvin unit. So before you substitute in the ideal gas law, take note that the temperature has to be in Kelvin and pressure has to be in atmosphere. And for volume, volume has to be in liters, which I gave you already the previous conversion for volume, just in case if it's not in liters. And for N, it should be in mole, which you know already how to get the mole from the mass using the molar mass. So now we're ready. I want you to look at this problem now. So this is the problem about ozone, the destruction of your ozone. How many liters of ozone can be destroyed at a temperature of 200 Kelvin and a pressure of 7 kilopascal if there are 55.0 grams of chlorine gas that react to it according to the following reaction? Cl2 plus 2O3 producing 2ClO plus 2O2. Checking the equation, is the equation balanced or not? Yes, it is. I want you to be able to check first if the equation is balanced. As to any stoichiometry calculation, you really need to ensure that it's balanced. So now, let's be ready. First, it's very important that you need to put the given because we have so many variables. What are our given? You know that we're given temperature, which is 200 Kelvin. No need for any conversion because it's in Kelvin. Pressure is in kilopascal. That's 7.00 kilopascal. But you know that you need to convert your pascal to atmosphere. So let's do the conversion now. Times, you know that in 1 kilopascal, there are 1,000 pascal. And you know that in 1 atmosphere, there are 101,325 pascal. So in this case, we will get up to two decimal places, so we will get zero point 0.07 atmosphere. So this is now our new pressure in atmosphere. And then aside from that, we're given 55.0 grams. So our mass, which is 55.0 grams, which we need to convert to moles because we need the moles in the ideal gas law. So that means we need to multiply this by the molar mass of your Cl2. Remember, this is diatomic. Chlorine gas is Cl2, so that means that's 2 times 35.45 grams. So that is 70.9 grams for every 1 mole. That's your molar mass of Cl2. So you will get the answer. Wait, because we let me erase this. Because we are getting the ozone, it's better that we do the conversion already. So 55 grams of Cl2, multiply it by the molar mass of Cl2, and because the question is asking us for ozone, that means we do the mole ratio right away so we can get the mole of ozone. So that is 1 mole in the balanced chemical equation, 1 mole Cl2 and 2 moles of O3. So you'll get 1.55 mole of O3. Okay, so let me stop there. I will continue in the next video as to how we approach this because of the time limit. So bye for now.